Welcome to In the Loop, a New England Temperature Solutions podcast. In today's episode, NETS Vice President of Engineering, Bob Pierce, will be interviewing our founder, Dominic DeLuca, on infrared technology. Dominic has been applying infrared sensors to thermal processes since the 80s. Without further ado, here's Bob and Dom helping you get in the loop.
Good afternoon, everyone. Today we're having a podcast on infrared technology, and we're here with Dominic DeLuca, President and CEO of NETS Incorporated. I'm Bob Pierce, and how you doing, Dom?
Doing good, Bob.
That's good. So, how many years has it been since you've been in the infrared technology market?
Probably 30.
30?
30 years, yeah. I got into it kind of by accident. We were selling thermocouples, and they added this line to the Barbara Coleman line at the time.
Mm-hmm.
It was a different brand than we sell now. Matter of fact, the brand we sell that I was selling back then doesn't even exist really anymore. They got bought. And it was a $4,000 thermocouple versus a $60 thermocouple. And I said, that sounds a lot more fun and like a lot more money as a sales guy. So
Sure.
I dove into it, and then I realized that it was more than just the money aspect. It was just a lot of fun learning applications, becoming good at it, and applying it to various places, and it added a lot of value to what we did, to what I did as a sales guy back when I was an employee of Barbara Coleman. But then when we started our company, it added a lot of value to the clients that we sell to.
Sure. Excellent. So primarily the infrared market that we're in is single point infrared temperature sensing. We do touch on some thermal imaging. We'll talk about that in a little bit. But on single point infrared temperature, we have a term called single color and two color, or some people call it ratio.
Right.
What's the difference?
So there's a big difference. One, it's more money. Good, but or bad because it's more money. People don't buy it. But so what a two-color or ratio is it's actually two detectors, and they call it two-color because it's looking at two different wavelengths. And the theory behind it is they found these two wavelengths that are offset, and that if there's an error based on emissivity, they will cancel each other out. So generally, like in the ones we sell, they're pretty much like 0.9 to 1.0 microns wavelength. And so a two-color unit has that formula and algorithm inside it that does that compensation for emissivity.
Sure.
The downside, and the reason why not everybody would buy it, would be one, price, and two, it has an elevated low temperature, in 600 Fahrenheit ish. So it's not good for low temperatures. It needs a high temperature and that's because there's two detectors in there, so there's only so much energy coming through the detector. But yeah,
sure. So I would assume then for lower temperature applications than a single color pyrometer.
Yeah, single color spot sensor. There's multiple wavelengths for a single color. You can get a 1 micron single color. Again, nothing goes to zero. Ambient in that range, maybe 100, 200 C. But the bread and butter for the single color market is the 8 to 14 micron, and that's kind of a wide range. It captures a whole bunch of stuff.
Sure.
And then you've got a 5 micron probably for glass. There's a 3.5 micron for like thin film, 7.9 for plastics.
Sure.
So what do you want to see through it? You want to see into it, and you don't want to see through the plastic. So there's various wavelengths for specific applications.
Sure. Now I've heard, of which obviously you're going to educate us on, that two color is really advantageous in atmospheres that have a lot of dust or smoke or off-gassing of the product inside of a vacuum furnace or something of that nature. Tell us a little bit about that.
Right. So a two-color, first of all, only needs a certain percentage of the target. So, I mean, you can read that says it needs 5%. I've never trusted 5%. So if I were to look at a light bulb, for instance, which we do a demo of a light bulb filament, which is extremely small, and that filament at maximum temperature is probably 3,000 centigrade. But if I were to, we've lowered the voltage and got it to around 1,500 C for our demo. If I look at the filament with a two-color unit and about 20-30% of the target is filled up through the camera with the filament, I'm going to look at 1,500 degrees centigrade right through the light bulb, because the two-color will look right through glass quartz. If I were to look at that same light bulb, our sensors let you look at the different wavelength readings. So you've got the two-color wavelengths, and you can look at them individually. It might read, the single-color wavelengths might read 600, because they're taking kind of an average of the field of view, which is maybe 20% hot and 80% cold. So so the advantage there becomes, the reason I bring that up is if you're looking through a window, we can look through quartz into a high-temperature furnace. But if a lot of times furnaces give off gases and dirt and contaminants that start to contaminate the window. So you'll be able to look through that window a lot longer without any degradation of the reading. And once it knows what the ratio is inside the unit, and once it gets to a certain point, it knows, game over. I've got way too much error here. That's the infrared for dummies that I have to know, because I'm not an engineer per se. But once it gets too wide, then we have that's how you detect a dirty window. When the ratios are so skewed, there's a percentage of degradation. We know that we have a dirty window. Right. So a two-color can detect that by monitoring the two wavelengths and their difference between themselves.
Sure. Now the product line that we sell, that we represent, Fluke Process Instruments, the Endurance two-color pyrometer. One of the great advantages of them is they can select between single color and two color.
Right.
Correct?
Yes. So if you pull up their software, you can actually look at the single color, the two color readings. You can look at each individual single color and two color, and you can see the difference. So one of the experiments we do with that, or test, is if you look at a black body, for instance, if you're calibrating it and you look at a black body, that means it's perfect. It's a perfect surface. There's no emissivity issues at all. All three readings should be the same. So if you're a black body at 1,500 centigrade, detector 1 should be 1,500, detector 2, 1,500, detector the two color should be 1,500. If those values start to move, we know that there's an emissivity correction going on, and we can actually determine whether a black body is defective or not, or going defective, by the movement of those two ratios and those readings starting to separate.
Sure. Interesting. Now, you mentioned black body. Ideally, with a single color, a single point sensor, ideally you should be looking at a black opaque surface.
Well, we know the yes and no. So, ideally, you could look at something like that, but the real world doesn't let you.
Correct.
So there is emissivity that needs to be determined. There's two ways to determine the emissivity of something. One is to look it up in a book. It says that this material is emissivity of 0.7, so you dial the 0.7 in. The other way is a little more less scientific, but probably more repeatable, is because there's a lot of things that go into it. Is to actually somehow take a temperature measurement with a contact, thermocouple or something, if you can, and adjust the emissivity until they match. Sometimes it's hard to do, but so if you can do that, you can get the exact emissivity, because there's a whole lot of things that go into the emissivity. There's the how smooth, how, like, my head would be really reflective today. Yesterday, before I shaved it, would be a little less reflective, right? So it's hard to really know the exact emissivity. But one of the issues with infrared that kind of saves us is the infrared is not necessarily for absolute temperature. Absolute temperature is evasive. If you want to know what the absolute temperature is of something, aside from like melting it and going to the melting point, knowing, that's the melting point, that's what the temperature is, you'd have to ask God, because it's really hard to measure absolute. The power of the infrared is it's extremely repeatable. So if you have a process and you know what temperature, how to get it to make good product, you can then set that as your operating set point.
Sure.
And it will bring you back to that exact same condition every single time. Mm-hmm. What happens, though, is people have been, for years have used infrared sensors that were not that accurate. So they had these like disappearing filaments, or they had older brands, and they actually did that, 10, 20, 30 years ago, and they said, we make great product and the temperature is 1800. Well, now they go and they buy a brand new Fluke, which is extremely accurate, which has 2-color technology, and that 1800 shows up as 1950, which is probably more accurate, but it messes up with their whole, we make good product at 1800. Well, with this sensor, you make good product at 1800, you're probably going to melt it, right?
Sure,
So there is some thought that has to go into changing, if you've been used to single color values that were probably wrong, but very repeatable, to what you'll use for a wavelength. So, and that's what we do. We look at your process and we talk about that and make you aware that you're probably going to have to update your sheets.
Mm-hmm. Mm-hmm. And you mentioned a word there about reflection. Yes. Are infrared pyrometers ideal for very shiny surfaces like polished stainless steel or something like that?
Yes, absolutely. If they paint it flat black, yeah. So I mean, think about we use a mirror to look around corners. We can get into really tight spots with a mirror. We shoot the pyrometer at the mirror. I've looked at a furnace that was like 25 feet away, the top of it. We had a mirror on the top, and we'd point our
right-angle mirrors.
Yeah, right-angle mirror.
Yep.
We'd point it right at the top, and it would, look down, and we got an extremely accurate temperature of what was reflecting in the mirror. So if you have a shiny material that you're looking at, so everybody asks us, we need to do these chill rolls or these heat rolls for paper and a web process. Well, they're going to reflect what's in them. And, if one of those little, these gas-powered like fork trucks go by, and it's got a hot engine, and it goes by it, and that gets reflected into the chill roll, all of a sudden you're going to have a spike in temperature.
There you go. Yeah.
And it's going to see that. Somebody walks by that's colder than it, and they reflect it, they're going to see it. So reflective stuff is extremely difficult. A lot of the applications that I say we definitely can't do are shiny stuff. I mean, we've tried to do some metals, and the problem with some of the molten metals is they're moving a lot, like bubbling, and there's agitation in there, and they can be very tricky. There is a feature called a peak picker, and you can average out a bunch of the readings and try to get a straight line and determine that. And people have used that successfully, where instead of an absolute, they get kind of a baseline of how it operates, which is probably a lot different than the actual temperature. But they know, I made a great part. That's where I want to go back to, and it'll bring you back there every time.
Sure. So again, the majority of our applications are single point sensors, looking through a window into a furnace or something of that nature. But then again, we have some customers that, all right, I have a rotary kiln. I want to see the temperature profile across my rotary kiln, or I have a motor bearing or something of that nature. What do we do then?
Okay, so the first thing people sometimes don't understand is you have to be able to see what you're looking at. So like in a rotary kiln, unless we had a window or a really good view of it, we have to physically, if you had a camera, just, if you couldn't take a picture of it with a camera, you're not going to read it.
Sure.
Right. But if you wanted to know the temperature gradient across something, so let's take a web, let's take this material. Years ago, we did a job that was this plastic, and we were looking for holes in the plastic. And with an imager, we can see small spots. We could, in this case, we actually used a scanner. So what a scanner did was it just kept drawing a line. So you would literally have this look exactly like your product on the infrared. And if there was a hole there, you would see this. It would show up like a meteor, because you'd have this plastic material, and all of a sudden it would look below it. It'd be really cold. It wouldn't be the warm plastic, and that would show up. And the beauty of the scanner was because it drew the picture. You could tie that together with position and determine, I have a hole in this general area, and through PLCs and software, you might be able to identify that hole before it ended up in a product.
Sure. Now, again, with thermal imaging, we have two varieties, 320 by 240 pixels and 640 by 480 pixels. What does that really mean to be able to sensing temperature?
So when you go with a 640 by 480, it's like having thousands of thermocouples staring. And with our camera, we're allowed to take, I think it's an average of 3 pixels. So you multiply 640 by 480, whatever that number is. I should know it, right? And you then have, divide that by 3, and that's how many areas of interest you can actually measure in the field of view, wherever it is. So you could actually, have hundreds of thousands of thermocouples and get an average reading. You can get the high temp and whatever it is in the field of view. So there's a lot of ways to get a lot of data out and see the temperature grading across the two. With software, you can draw histograms and graphs and actually look at the profile across. So if you've got this product that is like, especially in the medical industry, they do a lot of web processing with some plastics, and it's critical that the web is the exact same temperature. The other thing that gives you is sometimes you can correlate moisture based on the temperature. If something's more moist than other, it might show up warmer or colder depending upon it. But the other thing you can see is thickness, because if something is thicker, it may hold the heat longer than something that's thinner,
that makes
and
sense.
you'd be able to see it. So the holy grail on a web process is measuring moisture. It's measuring maybe thickness, determining it. It's not used for a thickness detector. That's really expensive, but it can give you an idea that you've got something goofy going on. And then you can also tune your furnace based on spots that may come out hotter or colder, based on what that looks like with the image, because you're getting a snapshot of the whole area.
Sure.
You can draw a line and get the high and the low and the average across it, and you can map it out and do a lot of not only like research and development on it, but you can actually control. You could actually have a zone control on across that and have that sent to an output to give more or less heat to a side of a furnace.
Cool. Excellent. So in your vast 30 years of infrared experience, what's the most strange or difficult application that you've had?
The strange one is easy. We were there was a guy who was he was tasked in Maine to count all the moose, and he had this idea, and he was bringing these drones in from, I think, Japan. And the funny thing is he disappeared. I'll tell you the rest of it, but he disappeared. And we tried to follow up after we did this demo that I'll tell you about. He just never showed up. And in the local paper here in Attleboro, it talked about this guy who was trying to do this, and he was in jail because the device he was importing was used for drug trafficking.
Oh my God!
And so what are the chances I'd read the paper for one and see it didn't name him, but it described him. But what he wanted to do is he brought me. It was a snowy night in the winter up in near on Golden Pond there in Holderness, New Hampshire, near Winnipesaukee, and it was a place where there were bears. And the first thing he wanted was me to see if I could detect the feet of the bare feet. And so we could. We shot the camera out, and we could see the paw prints. They'd light up a little bit, and they'd decay pretty fast as they got. But his number one thing was he wanted to see the bear pee.
Oh my word!
And he wanted to see what happened when the bear, took a leak, and we saw it and videoed it on VHS, and I'm pretty sure it ended up in my kids' school. We played it for the kids at some point, but that was the most bizarrest that I'd ever come across. As far as application-wise, there's just so many that are out there. I mean, it'd be hard to pick one.
Yeah, true.
They're all difficult if you put the wrong product. We have a pretty good toolbox, so if it can be solved with infrared, chances are we can solve it.
Excellent. Well, thank you, Dominic. That was enlightening. And
Bob?
yeah, absolutely. And if, again, our product that we handle for infrared technology is Fluke Process Instruments, and it's an excellent product, and look forward to assisting you in the future.
Yeah, thanks.
Thank you.
Thank you for getting in the loop with us. We hope this podcast was informative, and if you need any assistance on anything in the thermal process industry, please feel free to reach out to us at 800-848-NETS. That's 800-848-6387, or visit our website at www.nets-inc.com to fill out a request for information form. If there are any topics regarding thermal processes that you would like to hear on a future podcast, please send us a comment. We hope you have an awesome day every day.